And we're back. Alright, so here we go, folks. Let's see. With this lecture, we need to talk a little bit more about intramembranous ossification, how to create bone from in between two membranes. And these membranes are typically going to be some kind of fibrous connective tissue. So besides intramembranous ossification, there's also endochondral ossification, where you are making bone tissue from within a piece of cartilage that has already been grown ahead of time. But this one, intramembranous ossification, is the means by which we typically make our flat bones. So things like skull plates, ribs, your sternum, as well as half of your clavicle is made through intramembranous ossification. The other half is actually made through endochondral ossification. So to make a bone, it doesn't have to be just one or the other. It can be both simultaneously. But the procedure goes like this. You're going to start with a series of mesenchymal cells if you're talking about embryonic intramembranous ossification. These mesenchymal cells are ones that have just been sort of sitting around for a while. They're stem cells. They're multiplying fairly rapidly. Let's go with blue here. And just sitting inside of a series of embryonic tissues, haven't been exactly given a job yet, but eventually they will. They will be told to become osteogenic cells. Osteogenic cells are the ones that are capable of turning into chondroblasts, fibroblasts, and osteoblasts, and we eventually do want them to become osteoblasts in this case. So these mesenchymal cells transform to osteogenic cells, and the osteogenic cells are now going to continue to multiply, but they will grow in a mass where they tend to surround one another, kind of like this circular fashion right here. And then the ones that are deepest, all of them are going to be making osteoid tissue that lies in between them. An awful lot of protein fibers, mostly collagen, in sort of a soft mesh that's going to be surrounding each of them and one another. And so this doesn't just have to happen in one area. It can also happen in other regions too. You can have another set of osteogenic cells transform to osteoblasts and start making lots and lots of osteoid tissue in between them. And since this is going to be happening in multiple regions, then eventually these regions are also going to start to mix and merge with one another. So you end up with sometimes larger masses of osteoid tissue between osteoblast cells. And so now you start to end up with things that look like cylinders of soft tissue. And of course it's not just going to be this one, it's going to be multiples, which means we're starting to create the beginnings of spicules and trabeculae, like you would expect to find in spongy bone. But it's still just made up of cells, osteoblasts, that have made their soft collagenous osteoid tissue between them, creating these cylindrical spicules and plate-like trabecula. Okay? So what happens next is that the osteoblasts here that are creating this osteoid tissue also release an enzyme that encourages the deposition of calcium crystals onto the collagenous osteoid tissue. So it's going to start to harden and calcify, which means that all of this cylinder now is going to start turning into bone material. And the cells that are inside of this, well, they get trapped inside of that bone material, which means that they're now going to be going through their final transformation from osteoblasts to osteocytes. Right? And so you end up with now a cylindrical column of what is spongy bone, because remember, there's not just going to be this piece right here, there's going to be pieces all over the place, which will have inside of them your trapped osteocytes, which we can now call, we're calling them osteocytes. They're trapped osteoblasts, but we're now calling them osteocytes inside of your spongy bone spicule. The thing is, there's still going to be osteogenic cells. Osteogenic cells are still going to be on the surfaces, and the surfaces of all these regions is where we're going to keep a population of osteogenic cells, so that some of them can then transform into osteoblasts. Those osteoblasts can then lay down more osteoid tissue and fill in the space in between them, so that you could start with the creation of spongy bone like this But then as you fill in the spaces in between your osteogenic cells turned to osteoblasts, then that column of tissue that you just made, that one spicule, is going to get thicker. And so the spaces between columns is also going to get filled up with more material. And so as a result, spicules can start to join together and holes get filled in. Which is why, let's bring up this image here, we can go from a state like this one, where initially you have your osteoblasts creating osteoid tissue, that's the stuff right here in between them, calcify and become a column of spongy bone. Right? There's your trapped osteocytes inside of it, and here we still have osteoblasts more forming osteoid tissue on their surfaces, and then one of those columns starts to join with other columns, like this one right here, and now we have a network of spongy bone. And if you just fill in the holes by growing more osteoid tissue on the surfaces where there is no bone, then as it gets transformed to spongy bone, it gets smaller and smaller and smaller, and so instead of having spongy bone, you now have compact bone regions. And still, wherever you find a surface, there will still be more osteogenic cells that can then be turned into osteoblasts, which can then lay down more osteoid tissue, and you can keep on adding more bone to it. But one of the key parts of intramembranous ossification is that you are very likely to end up with a layer of compact bone, a layer of spongy bone, and then a layer of compact bone on the other side. And wherever there's a surface, you will find more osteogenic cells that can become osteoblasts and make more osteoid tissue. But there you go. That is how you're going to end up with this sandwich-like configuration of spongy bone. Compact on the outside, diploid in the middle, if you're talking about, say, skull bones, and then compact bone on the other side. This pathway is a common one throughout all of your bone creation methods. Intramembranous, obviously, but it's also a key part of endochondral ossification, and when you're going through bone fracture repair, you will still have to go through this sequence of events. Osteogenic cells become osteoblasts. Osteoblasts lay down osteoid tissue, soft collagenous tissue, that then calcifies to become spongy bone, and then if you need to, you can fill in the holes and turn spongy bone into compact bone. But what if you need to get rid of bone? Say, for instance, that you need to burrow a hole into the bone in order to allow a blood vessel to penetrate. Or maybe you need to clear out the space inside of a long bone so that you don't have spongy bone filling the center, but instead have an empty medullary cavity where you could then grow bone marrow, yellow bone marrow or red bone marrow. To get rid of spongy bone or compact bone that's already there, that's when you're going to need osteoclasts. Osteoclasts do not come from the same cells that osteoblasts do. Osteoblasts come from osteogenic cells. Osteoclasts come from a series of stem cells that are found in bone marrow. They're the same kinds of cells that give rise to red blood cells and white blood cells. But these cells then merge together, a number of them, to become a massive multicellular bone matrix dissolving cell, and that is your osteoclast. So any bone remodeling that you might need to do will be done with osteoclasts. Any bone growth that you need to do is going to be happening thanks to osteogenic cells becoming osteoblasts, osteoblasts laying down osteoid tissue calcifying to become spongy bone. Then you can fill in the holes if you need to form compact bone, and then you can remodel it once again with osteoclasts if it's absolutely necessary. So those are the main steps of intramembranous ossification. And so I'm just going to cut this video short right here, and then go on to endochondral ossification in the next one. Right? So, bye-bye for now.